in this portion, we are going to cover two things. One is interoperability and the metadata and provenance. Now, you have already seen some things in the previous section and others where we have alluded to, why we need this kind of thing and what is the purpose. We will try to understand more of what are the things that are needed, what things have to be in place in order to do this. So that's me. And again, I'm not making any assumptions. I'm let you know so that hopefully you, even though you might be familiar with a bunch of stuff that I'm going to cover. So we cannot sort of discuss interoperability without understanding a little bit about standards and integration and how they are different from interoperability. If we look at some familiar examples, I'm sure you have been using a bunch of things without even knowing how they work together and why and how they were made to work together. So that's important to understand our daily things that we use. So the other question is, why is this important? We will look at a video. I think it's a very educational video, bringing out clearly the need and the difference between integration and interoperability. Even though it's for healthcare domain, it's applicable to, in my opinion, other domains as well. And then we'll go into some details, application interoperability, data usage, and finally, how trade principles, which is the kind of the basic underlying theme of this workshop, how it affects interoperability and what is the relationship between them, some conclusions. So standards, integration, and interoperability. So everyone has heard of standards. We use that in our daily life, something set up or established by an authority as a rule for the measure of quantity, weight, extent, value. So we know what 1 pound is. There is a standard as to how much a pound is, how much a kilo is, how much is a meter, and how much is a yard. All those things are established and we use it routinely, take it for granted. So one other example I will try to give is, so standards constituting or conforming to a standard, especially as established by either law or custom or a community agreement to do so. And you can see the prevalence of standards in various domains. IEEE is an Institute of Electrical and Electronic Engineering, ANSI, ISO 9000, ASCII, OGC, which is related to your domain. So every domain has different standards for different purposes. So some of the examples that you have used on a regular basis, we all use USB compliant devices. We also use disk devices that are set on SCSI compliant. You might have used XML, which is a data exchange standard, HTML, which we are all familiar with from the web. SQL is a standard. So we are familiar with a lot of these things on a daily basis and use it, but we don't perhaps think a lot about why they were developed, what was the purpose, and what happens if we don't have them. So following a standard has a bunch of benefits. So that is certainly true. If each one did according to their own way of thinking, then it will be very difficult to do any interaction or exchange or business or commerce or any of those things will be very difficult. supports multiple things with a standard interface to connect and interact without any additional effort. So this is the key or the purpose of a standard. So you should be able to use it without having to worry about it. A very good example, I feel, is the way we have clutch and brake and accelerator in an automobile. So just think of a situation where this was not standardized, or every manufacturer was using a different way of doing it, even different locations for them. There would be a total chaos. So even though we don't think about these things when we use them, this is a standard that has been accepted in whatever way, whether by the community or by law or whatever it is. This is one of the very useful and important standards that make our life and everything else much easier. So that's important to understand the purpose and the utility. So what happens if you don't follow the standard? So we are also aware or familiar with some of these in our daily experience and life. And here are a couple of examples. Electrical connection. For whatever reason, different countries have decided to come up with a different standard for historical reasons for their own country. And the downside of that is you have to carry converters when you travel. It would have been nice if the whole world, like the cars, had the same thing. Another good example is, Apple having its own interface, which is not compatible with anything and anybody else. So people like European Union is trying to fix that, sort of making them conform to a standard interface. So that's very important. So you can see in our daily life what happens if we don't have a standard, and what are the effects of that. I was surprised to read that there was a fire in 1904 in Baltimore, and it was a disaster, partly because 30% of the hoses would not connect to the thing that they were supposed to connect, which essentially state the standardization either was not there or was not being followed or enforced or being used. So this is a tragedy, right? This is a tragedy that can be avoided by making sure standards are followed and used correctly. So you might have heard of other things like standard wars. One famous example I can think of is Betamax versus VHS. So this is between industrial giants who wanted to make their innovation the standard for everyone. And again, some of these are not necessarily decided based upon the technology and other things, depends upon various other factors. But this goes to the essence of understanding why standards are useful, because then you have to make a choice when you buy something, whether it can you can use this particular product or this other particular products, or you have to buy multiple ones. So standards are very important and very integrated in our daily life. So our interest in standards is in slightly different purposes, using available data. We want to use available data, and what happens if we don't have standards for that? Sharing data. So it's very common, as we saw in the previous examples, when you have multiple files or multiple types of information that you have, they need to be merged or shared and combined. And that is going to be an issue. Application interaction. So we'll see more of this. If applications need to interact, they need to conform to something. That means one has to understand what it is. I mean, think of it as a natural language. If somebody speaks Mandarin to me, I won't be able to understand. So I do not understand that particular format or that particular language, and vice versa. So this is very important even for an application, because they will exchange communication data. data integration, application and data integration in general, and interoperability. So standard is applicable to both data, applications, and we'll see it can even be applied to metadata. We'll see metadata creation in the afternoon, and you will see, there has to be some uniformity with which metadata is created. And the question is, who is responsible for creating these standards and how it is done? So it is typically an entity such as IEEE, ANSI, or OGC who come up with this, with consensus with the right background. So there can be something purely based on consensus and usage, or it can be an evolution into what it has come to, and everyone understands it and uses it, so it's no longer a problem. So you can also apply the notion of a standard to a software in addition to devices and other things. A software standard is a standard protocol or other common format of a document, file, or data transfer accepted and used by one or more software. So essentially, this is a standard in order to make sure that one software can understand the lingo from the other software and vice versa. And without that, we will be developing software independently, and it will be very difficult to integrate them or communicate between them. So standards are also critical to the understanding compatibility of hardware, software, and everything in between. Industry standards enable the essential elements of a computer and related infrastructure for that purpose. So you will see, network standards, or other kinds of standards that are commonly used. Standards typically allow technology to work seamlessly and also establish trust for smooth operation. It can provide a common language, makes interoperability of the components created independently. That's very important because we create a lot of things independently without knowing who is going to use it or how it is going to be used. And if it has to be used in a meaningful way by a large volume of people or masses, then it has to conform to certain standards so that it can be used very effectively. It also guarantees behavior that's well understood. So when you know what a USB-A is and what a USB-C is, you know the difference between A and C, and you understand the behavior very clearly. One is faster, one is not as so fast, and compatibility and other issues apart from that, you understand it very clearly. Sort of one interesting side note is, apart from the standards for application exchange, even when you develop software, one of the biggest challenges for software engineering people is how to make sure that the software is understood. Not just the interfaces, but the software itself can be understood. This is very useful from a developer's point of view, right? I mean, there are people who use the software and there are people who maintain the software, who extend the software, who revise the software. So these are two different groups of people, and you want to make sure that there are standards or perhaps guidelines to do that. So Java was the first programming language that introduced for the first time in a language what to do for generating documentation automatically. Until then, documentation was separately created by developers. And as we know, most of the times it is not done. It is done after the fact and it's not captured completely. And the cost associated with software is mainly because of this reason. There's not enough documentation. So sometimes redeveloping things is cheaper than fixing something that is very difficult to understand, especially if it's complex. If followed, this made it, there was no need for a separate documentation. And based upon my experience and others, people rarely do documentation properly, and that is the biggest problem. So here is a example of guidelines. You can sort of sprinkle various comments and other things. Comments have been around, but comments themselves do not create any additional document. So here, for example, some of the things that are highlighted in bold letters is primarily meant for a software that could go through this code and generate appropriate documentation for the use of this software. And this is very important. I don't know, I mean, at least in the computer science and software engineering, we struggle a lot about this. We struggle a lot because documentation is very poor, and even when it exists, it is not complete. And that makes very difficult to maintain, manage. Just to give an example, Oracle DBMS, for example, is 1 million plus lines of code. So this has been developed over the last 40 years. So multiple groups of people have implemented, revised, extended, and do that now. There's a new batch of people who have to maintain and extend that. And for that, understanding the current code is extremely important before we make any changes in a product that is being used by hundreds of thousands of people. So that is the uh, so uh, uh, agencies like NASA worry a lot about software quality and trustworthiness, because when they send somebody up, they want to make sure that the software works the way it should work and there are no other things happening. So here is, so once you put in the right information that is according to the guideline, this is what you get. Here is an example of what you get. So this is automatically generated. This is an example that we use for a software that we use for Minibase, but you can find this for a lot of different kinds of software, primarily developed in Java. So it tells you what is the class, it tells you what object it is, it tells you, uh, uh, so it can give you class use, whether it is duplicated, index, and all things. And so it will tell you what are the fields associated with this class, what is the constructor, methods associated with that, and various other details that you can look at. And this can be done without having to write a separate documentation. To me, this is one of the most important, and then you can dig deep and go into the details of each one of them. And so this assumes that some guideline or some standard has been followed in the creation of these things, without which this cannot be done. So that is the sort of the importance, as I see, in terms of why these are important. So just to, in a lighter vein, how standards proliferate. So certainly we have a lot of standards, and you have some number of standards, and you feel that you need a universal standard. Now we have one more standard. So I, also there is a saying that goes this way. The good thing about standards is that there are so many of them. So apart from that, I think standards we understand, we see that is extremely important, extremely beneficial, and every attempt should be made, at least in the software domain. So I just want to contrast this with hardware domain versus software domain, because there is a big difference when chipsets and chips are manufactured. Standards are enforced very effectively, because if it's not done, then there is no way to use it, and there will be heavy losses. Whereas when it comes to software, it's a very tricky thing, because software can be changed on a daily basis, whereas you cannot manufacture the same Intel chip on a daily basis. You can manufacture, but you don't revise it. You revise it periodically, and the new version is out there for a year or two. So that is not true for software. The ability for us to keep changing them incrementally, and whenever we want, makes standardization much more difficult, makes the cost of software development so much difficult. Any questions so far? Okay. So now let's come to integration. So standards are mainly used for a specific thing. Integration means you are connecting or integrating something with something. Following standards allow us to connect or integrate devices easily. However, we are dealing with not only devices, but data, software, and applications. So it's not just a two piece of hardware for which standards are, I think, much more understood and enforced. Although there are guidelines for software development, rarely applications that are developed independently can work with each other. Whether it's exchange of information or calling one from the other without any additional support. This is the key. When you want to integrate, you need to make sure independently developed software can work together. And if they don't, then you have to provide some additional support. This requires integration of applications that are developed independently. And what does it mean? It means that for application integration, the issue is the data generated and consumed by an application has to be properly dealt with. As data can be generated in many formats, it can be in a binary format, it can be in a customized format, XML, JSON, data exchange formats. You need to worry about that. Consuming data by other applications requires additional software to understand and interpret it. So when you make a call and send certain pieces of information, the other side has to understand and interpret it so that it can make use of it properly. This is usually done by integrating the two applications by adding appropriate new or additional software in each application. So essentially, you add additional pieces of software that is capable of understanding what is sent by A to B and B to A so that they can exchange information in a way they can understand each other. So the difficulty or the cost is this may have to be done for each pair of applications. So if you have only two applications, maybe it's easier to do. But if you have 5 applications, then the number of such software pieces that have to be developed for each one to understand all the others is going to become extremely complex. And this is typically referred to as the quadratic cost. So as you know, quadratic curve, which is a square curve, it rises much faster than a linear curve. And here is a sure. So this is not, so you can think of a linear curve, which is typically at 45 degrees angle, and that increases. So when the number of applications increase, the number of things you need to do is linear, place 1 to 1. If you have 5 applications, you need to do 5 things. But if you are doing the quadratic, then the number of things you have to do increases significantly to the power of 2. This is the problem with integrating applications on a pair-by-pair basis, which is extremely difficult to do. So this is the underlying problem and the cost associated with it. So software development cost, not only is the development cost, testing, debugging, making sure everything is working out. So software integration can be thought of as the process of connecting one piece of software application with another, typically through their application programming interfaces or what we call APIs. So typically applications publish their APIs so that some other application can call it without having to know the details of the application, which may be proprietary in nature. In many cases it is. So APIs are a mechanism to publicly advertise or publish what interfaces they provide so that you can use the system or use the software using those APIs without having, so essentially it's a black box model. So in a black box model, you don't know, or you're not allowed to know what is inside the black box, but you know how to use it. You know how to operate it. You know how to connect it with other systems that will work together. So that is the whole idea. So once connected, the applications can share data and provide updates to one another in or near real time. So that is needed in many cases. This could include integration with data repositories and different types of databases, because if you access data from a database, you have to use an API, for example, for that, and then get the information in whatever format it sends it, understand it, and utilize it. Here is a simple example that you can relate with. So earlier I mentioned something called market basket data. So this is what we call the point of sales data that is typically collected by every vendor for every customer. So every time a customer walks through a shop, buys certain things, checks out at the counter, these points of sales information is collected. This essentially says, this is the location in which this was bought in this particular counter, and these are the items that were bought, and this is the price of these items. You also have separately customer information with the vendor as part of our system. So we have all these cards for demographic information and things. And to understand the customer preferences, you may want to put these two together. So maybe one application is dealing with the points of sales, generates the data and makes it available in some way. Another application has the customer information. But if you want to put these two together, then you have to build some additional software at both ends in order to do that. One way to do this is through APIs and understanding the individual data formats from the application. So this is just one example. You can think of very many places where this kind of thing happens, because not all data is collected in one place and stored in one format, stored in one application. So let us take a look at the above concepts leading to the concept of interoperability. Why we are not happy with integration? Is there a better way other than integration to deal with this problem? And we're going to watch a video to understand that. I think this is a good video that brings up. Although this video is from the healthcare domain, I think it's easy to understand the underlying problems, issue, solution, and its applicability to other domains. The principle explained in this video may be applicable to different domains in different ways. So let's take a few minutes to watch this, and then we'll discuss this.
I don't know if there's supposed to be sound, but I don't hear any sound for the video.
Excuse me?
I don't hear any sound for the video. I didn't know if there was supposed to be any.
There is, the audio is very important. How do I make it come through?
I think when you're sharing your screen, there's a checkbox for sharing computer sound. When you go back to the share button at the top, I think.
Okay. Right back when two computers from exactly. Okay. Okay. I think now I have done that. Let me start this from the beginning. Tell me whether you.
Standards and interoperability in digital health.
Yes, it's coming through.
Explained.
Okay.
When people discuss digital health, the terms standards and interoperability often come up. What do they mean, and why do they matter? Could such abstract technological processes actually help save lives? We will answer this question in 3 parts. First, we will look at a case study to explore why it's important to get digital health applications to communicate with each other. Second, we will see how connecting digital health applications through integration leads to significant cost, scalability, and management challenges. Third, we will show how to overcome these challenges through standards and interoperability. Let's start with part 1, the case study scenario. In the fictional country of Onessa, Lucy, the National Immunization Officer at Onessa's Ministry of Health, and Isaac, the District Health Officer of Umbaya, are planning an upcoming child vaccination campaign to get child immunization numbers up nationally. Lucy has been put in charge of managing the national campaign across all the districts. She starts by working in the most populated district first, Isaac's district of Umbaya. Isaac's district includes some rural areas as well as some smaller city centres, and in this campaign, he will need to provide immunisation to children in all areas of his district through facilities and mobile clinics. Lucy visits Isaac's district health office to help him gather the information he needs to do his district planning for the child immunisation campaign. They want to use 2 different data points to assist with planning. The first is they need to know how many children need to be vaccinated. The second is they need to know how many vaccines Isaac currently has for each of the service delivery sites. If they can't compare this information, they might not order enough vaccines for the children in his district, putting their lives at risk. These 2 data points exist in 2 different global goods applications: Open LMIS, a supply chain application, and DHIS2, a district health information application. Open LMIS can give them a view of the vaccine supply chain, how many vaccines are available to be used, and where they are stored. And DHIS2 can give them a view of the number of children in the district catchment area who are eligible for vaccines. But they can't see this information together because it is in 2 different applications. Currently, to analyze the data in this format, it takes significant manual labor, and even still, sometimes the data sets do not align properly, resulting in less reliable and error-prone information. Ultimately, all this tedious effort leads to too much time managing and cleaning large and often inaccurate data sets, and not enough time making evidence-based life-saving decisions. But why can't these 2 applications automatically exchange information with each other? Well, when Open LMIS tells DHIS2 there are 5 DPT vaccines in Umbaya Clinic this month, DHIS2 cannot understand Open LMIS's shared messages because they use different vocabulary and grammar to describe the same data values. So how can we help people like Isaac and Lucy get these systems to communicate? Let's explore that next. In part 1, we saw the challenges faced by health system managers trying to make digital health applications work for their health programs, and left off with Lucy and Isaac struggling to get their applications to exchange data. Now in part 2, we will examine the way Lucy and Isaac initially try to solve this data exchange challenge, but face problems with this approach later. When talking to the ministry's software development team, Isaac and Lucy learned that they can directly integrate the 2 applications, DHIS2 and Open LMIS, to enable communication of data. They explain that to integrate the 2 applications, they will need to write custom code between the applications to translate how the data is being described by each application using a bidirectional connection. This sounds like a good strategy for solving this simple use case. However, Isaac doesn't just manage immunization, but all the health programs in his district, many of which are supported by their own applications that could benefit from communicating with each other. And Lucy doesn't just work in this district, but manages the whole country's immunization program. And she needs many other districts' applications to be able to communicate as well. So Lucy and Isaac asked the software development team about integrating their other applications. When working with the team on integrating the larger set of applications, they encounter new challenges. When they connected just 2 of their applications, OpenLMIS and DHIS2, they needed just 1 bidirectional connection to exchange data, so the cost was low. However, this problem compounds when you add additional applications. When they add a 4th system, they need to maintain 6 bidirectional connections, and a 5th needs 10. And if one application changes, all the other applications need to change as well, since they are now connected. This is extremely expensive and will quickly use up their entire budget. Why does the cost and complexity rise so significantly with each additional application? The software development team explains that it is due to a problem known as the quadratic cost problem, named after the mathematical concept they illustrate here. The number of bidirectional connections increase quadratically, not linearly, with each integration of a new application. When you have a country with as many systems as Onessa, by the time you need any more than 3 applications, the cost and complexity rise much faster than the number of digital health applications you are trying to connect. There must be a better way. Integration is not sustainable. Writing software to directly connect to applications, or integration, may be able to connect your applications, but there will still be the quadratic cost problem. Is there a way for multiple applications to communicate with each other that addresses the quadratic cost problem? Yes, we will explore this in the next part. Now in part 3, we will see how Lucy and Isaac learn about investing in an approach that addresses these challenges and allows multiple applications to exchange data. The software development team explains that the solution is standards and interoperability. First, they show Lucy and Isaac what standards are, and then they explain to them how it will help with interoperability. What are standards? In software, standards are a set of rules that allow information to be shared in a uniform and consistent manner across any application. They are approved and published by an authoritative official organization. As the systems are currently configured for Lucy and Isaac's immunization campaign, OpenLMIS and DHIS2 cannot currently communicate with each other. Remember, DHIS2 has been trying to ask OpenLMIS a simple question: how many DPT vaccines are at Mbaya Clinic this month? But they cannot understand each other without a common set of standards. The software development team instructs Lucy and Isaac on the importance of 2 specific types of standards to enable interoperability: semantic and syntactic. Standards that help applications establish a common vocabulary are known as semantic standards. For the 2 applications Lucy and Isaac are using in their immunization campaign, they need to agree on 2 vocabulary lists in order for the applications to communicate, one for the vaccines and one for facilities. For example, the semantic standard to refer to the DPT vaccine is vax.dpt, and for the Mbaya Health Facility is Facility 145. Once they agree on a semantic standard, they both use the same terms to describe the same commodity. When DHIS2 asks OpenLMIS, how many vax.dpt vaccines are at Facility 145 this month, OpenLMIS responds to DHIS2 with a question: what do you want to know about vax.dpt and Facility 145? With semantic standards, even though both applications are now using the same words, OpenLMIS still doesn't understand what is being asked. OpenLMIS can understand the vocabulary of vax.dpt and Facility 145, but not how they relate. Knowing what the terms mean isn't enough. So the software development team explained to Lucy and Isaac that these applications also need to have common grammar to communicate meaning. Standards that do this are known as syntactic standards. They help you determine how the words fit together. The software development team shows Lucy and Isaac what happens when they have both semantic and syntactic standards. With both sets of standards in place, the DHIS2 and OpenLMIS applications can share data automatically and seamlessly. So when DHIS2 asks OpenLMIS how many vax.dpt vaccines there are at Facility 145, OpenLMIS can provide DHIS2 with that data, responding that there are 5 vax.dpt vaccines at Facility 145. Now that Isaac and Lucy understand standards, they must determine all the different semantic and syntactic standards they would like to adopt in ONESA. The software development team explains that investing in standards will make it easier and more cost-efficient to enable interoperability between all their digital health applications. Interoperability is the ability of multiple applications to communicate with one another by accessing, exchanging, and making use of data in a coordinated manner to achieve health goals. To ensure true interoperability at a large scale between all their systems, Lucy and Isaac learned that they need to invest in a component known as a Health Information Exchange. A Health Information Exchange, or HIE, is part of a country's enterprise architecture that connects multiple applications and allows them to move data between one another using standards bundled together to provide implementation guidance for the software developers. This approach overcomes the quadratic cost problem. OpenHIE is an example of such an architecture. One of the things that HIEs do is store lists of terms and concepts, mapping how these lists relate to each other across different applications. Standards make this mapping process easier. The HIE receives the data from each of our applications and keeps track of how they relate and will translate between the different applications in real time. This enables the 3 or more applications to communicate through our HIE as a central translator. Now, any new application that gets added only needs to be able to communicate with the HIE. And if an application changes, only the HIE needs to be updated, while all the other applications can still communicate. This is one way to keep costs down and avoid the quadratic cost problem we saw in Part 2. Now that Isaac and Lucy understand how standards let applications communicate, both vocabulary and grammar, and that an HIE lets many applications easily exchange data in a cost-effective way, they want to invest in building one, and are ready to learn more about how the components of an HIE architecture can interact with their applications. Once they know this, they can work with the MOH's digital health lead to ensure that the investment roadmap for their national HIE will meet their needs. The next year, when Isaac and Lucy need to do their planning, they can pull the data they need from the different systems together. This lets them see how many children need to be vaccinated, how many vaccines they have available, and how many they need to order. With their applications linked, Isaac and Lucy can ensure that all the children in their district and country are vaccinated and can grow up healthy. Moreover, by using an HIE to help interoperate their applications, data is showing them population-level trends they couldn't see before, and now they can make time-sensitive, evidence-based decisions that impact the lives in every district, at every age group, and at each point of the health journey.
Okay, so I want to pause here for a second to get any questions or comments. I'm assuming that this has clarified a bunch of things about standards, integration, and interoperability. Any questions? Okay.
Standards and interoperability.
Okay. So let's continue with what we're doing. So another easy to understand example is, think of a speech given in UN General Assembly in a specific language. To translate this language to different languages, you need one interpreter for each language into which it is translated. So this is typically integration. And if you want to do it for many languages, you need so many translators. And this number goes up if there are 5 different languages being spoken, and it has to be translated into 5 other languages. Alternatively, it can be translated into a single common language if possible, if everyone can understand that common language to provide interoperability. So kind of this is the essence of interoperability and the middleware or the exchange that you saw in the video. So in order to do that, some effort is needed, but that effort is much less than the pairwise integration of doing things. So integration makes sense if you have a small number of applications to work together, but the quadratic cost kicks in when the number of application systems to be integrated gets large. So that is really where the utility of developing either an exchange or adding a middleware that can translate from one to another is extremely beneficial. So interoperability is preferred for a large number of applications, less resources needed, and scales better with different types of data being used, generated by applications. When a new application is added, it has to only understand the common language, not every other language. So that's the main idea behind it. System or software developed for this term is many times called the middleware. And the goal is to reduce the quadratic cost to linear cost. So how important is interoperability? So here is an example that I can sort of relate to. In the 70s and 80s, the Department of Defense was using hundreds of programming languages in its units. Air Force was using few languages, military was using another few languages, Navy was using a different set of languages, and each one was developing things in their own languages, as well as multiple databases. So this was another issue. There was a lot of effort. I was part of some of them. So they were using relational databases, hierarchical databases to do different pieces of information. Sometimes same data or information was stored in multiple databases using different attribute names, making it difficult to understand the semantics, just like the semantic exchange that we saw, structure and semantic standards. It's not enough to just think about structure. The vocabulary should need to be same. If something is called, ship ID in one place, SID in another place, you don't know that ship ID is the same as SID. So this was a real problem because lots of research came about on schema integration, heterogeneous and distributed DBMS to overcome this problem. So schema integration was done for a long period. How to take schema from the different, even relational DBMSs and figure out how to merge them to a single view that can be useful further. So this was a real problem that was faced by DoD and things have changed. So millions of dollars were spent on this. So some of the things DoD did was so there was inconsistency as well as different names. So missions. So when you think of missions that are the DoD essentially they create what is known as wartime and peacetime missions. These are done way in advance and kept, and they're periodically evaluated for their execution, and they use resources from multiple branches of DoD. And so this was very difficult to do in the presence of information being scattered. So schema integration became an important topic. Heterogeneity of data models had to be addressed. Heterogeneous and federated concepts were explored. Another kind of civilian example you can think of, which was widely used in some of the research was, all of you are familiar with restaurant view systems, right? And in order to show you the review or Michelin review of restaurant systems, they have to pull data from multiple sources. And these multiple sources are independently developed and do not contain the same information or the same format information or even the same vocabulary. So that has to be in some way reconciled by this middleware that brings all of them together to do that. Prototypes and systems were built to demonstrate the concepts. So, so what DoD did to alleviate this problem in some ways, they initiated the development of a new programming language to be used across all branches of DoD, and it was named Ada. I don't know how many of you are familiar with it. And Ada as a language was named after the lady Ada Lovelace, who was the first woman computer programmer, and was developed in 1950. So this was a long effort. It took like 10 years by a committee, European, American, and others. And they looked at different programming languages, looked at different requirements of DoD, and then figured out, what features this language should have and why it is important for the purpose of DoD and things. So it was a huge effort. And at the end, this language became very bulky. They have added so many features from so many different languages that it became big, but it was completed. Compilers were developed, even a new company was born, Rational Rose, that only implemented Ada on machines and then sold it. Ada is currently used across DoD as the application development language. Unfortunately, it's not widely used outside of DoD. Another thing they did was they also funded the development of Oracle relational database in the 80s. And this DBMS is very widely used across it, at least a single model instead of using it. But still, the issue of making sure that the vocabulary is the same and the attributes can be identified and they can be merged is still a problem that has to be addressed on top of that. So it's also a very popular DBMS with the highest market share. So there has been a lot of instances in real world where interoperability or inability to have systems interoperate was a big hurdle, and a lot of mistakes and other things happen because of that. So another example for making it easy, we routinely use Google Flights and other similar systems for exporting flights. Everyone uses it. So how does this work? Again, this requires access to multiple independent data sources. And like they have to access American Airlines, Delta Airlines, all different airlines, and they have their own independent. It's a black box, as I said. They provide APIs to query a particular flight and then get information about that and the cost and other things, but they cannot see the algorithm that is used behind it. Output from these may not be the same. How is a single integrated view provided for this? So what we see is a single view, irrespective of which airlines, which tells you in a nice way how this is essentially is a good example of interoperable systems using a middleware. Here, perhaps they don't use a data exchange format that is agreed upon, but the middleware understands each one's output and tries to convert it into a common thing because they're not sending information from one application to the other, but it is being consumed by the end application for you to provide that information. So a little bit simpler. So since we are discussing provenance later, the provenance for this kind of effort was started by a few graduate students in Stanford in the 80s, early 80s, I would say. They thought about this particular problem and came up with a prototype system, which they then sold it and became venture capitalists. And then everyone experienced it, Travelocity, you name it, every web GUI provider who does this kind of integration uses interoperability principles underneath. Surprisingly, you might have noticed that Southwest does not allow this, and hence that information is typically not available. When you go to these places, you will never get Southwest flights. You have to go separately to their website and look it up. And that is because they don't publish their APIs for these people to use. So again, all those things are part of the interoperability things that we're discussing. Any questions? Okay, so there are different levels of interoperability as we understood from the video. So there is something called foundational, which is tightly integrated, does not require the ability for the receiving system to interpret data. They communicate in the same way. Structural refers to structure or format of data exchange, defines the syntax of the data exchange. Semantic, ability of the two systems to exchange information, use the information that has been exchanged using a common vocabulary, sometimes taxonomy, and that's very important for interoperability. And sort of typically semantic includes structural interoperability, and that is the highest level of interoperability, highest level of interoperability. So this should have been clear from the video. So finally, what I would like to do is, okay, how does all this relate to FAIR, which is the underlying theme for this workshop? So from open to FAIR. So open data is available without restriction, but there is no guarantee about how it has been generated and what format it is in, and all those things are not there. Whereas FAIR data defines specific conditions to be accessed and utilized. So these are known as the FAIR principle that you already seen in the earlier tutorials in this workshop. You can certainly apply the same principles to metadata as well if need be. On the other hand, FAIR data is also widely available and utilized by incorporating the following usability requirements, which is not available or not worried about in the open data. FAIR data must be defined and entered into online public records for the purpose of discovery and solution. So the first step in the use of any data is to find such a data exists and being able to discover it in some means, whether it is using a URL or using a set of keywords that are associated with that data set or a citation. It doesn't matter, but it should be discoverable. FAIR data must be made accessible such that it can be open, read, and processed. So certainly proprietary data that is not available is not FAIR data. FAIR data must be recorded and represented in a way that can be understood and utilized. That means there should be sufficient metadata associated with the data for someone to consume it in the right way. Data interoperability is the ability of data set to work with other systems or data sets without special effort. So data interoperability has also been defined as a feature of data sets whereby data can be easily retrieved, processed, used, and it is not very different from the FAIR principles. Above characteristics of data is clear that metadata can exist for both data and data sets as a whole. So how do you facilitate interoperability? One of the ways is through data exchange formats. So if you use a data exchange format that is a standard format, then the other system may already have support for that. So typically, when you have a popular data exchange format, a lot of different systems natively provide support for that, so you don't have to add or integrate that piece of information. So using a standard or known data exchange format makes it easier for applications to facilitate interoperability. Support for known on agreed-upon formats can be built into systems, which is done for these systems to be used widely. A transition from earlier binary exchange to a human readable. So this is important. So what we have seen is that before all this interoperability and other things, the only way systems exchange was through binary data. So someone would write a file, the other one would read a binary file, but one had to know exactly what is contained in that file to understand and use it. And the most difficulty with that was that it was not human readable. So when somebody wants to exchange any invoice and somebody wants to make a payment, if all of them are coming in the binary way, then it's very difficult to see and understand for a human what is happening. So human readability became very important. And with human readability, it is possible to understand for someone what it could be, also be able to be processed by the computers and how to do that. So typical languages, so these markup languages became popular. HTML, XML, RDF, XML, you might have used some of them. HTML especially is the one that is used for web, for example. And this was derived from, surprisingly, the proofing way in which documents were proofread and annotations that were made. That was one of the markup languages that became extended to HTML. So common data exchange languages are the following. It's not a complete list. XML is one of them. You might have used it. JSON is another one, which is kind of different from XML. AML, yet another markup language. CSV, TSV files. RDF is more used for metadata. We'll see more of that in the next session. Next. We are already familiar with CSV and TSV. TSV is tab separated. These format files can be used directly in Python and other libraries used by Python because Python supports these formats natively. So you don't have to add any additional piece of software, and you can import these things directly into the data structures in the language. Metadata is still needed for understanding how you need to analyze them. So you may get a data file with lots of data, like we saw in the census example or in the other application I showed you, but you need to understand what they mean. So semantic or at least structural for using them. There has been a conscious move towards human readable formats. So briefly, just looking at some of the advantages and disadvantages of these. So XML, the acronym comes from Extended Markup Language. One is it's very flexible. Uses standard published by W3C, which is the World Wide Web Consortium, and various working groups. It's human readable, although not very easy, but readable and editable. Error checking by using STDs, display using style sheets, DTDs. So there is a lot of support. There's a lot of development utilities around it because this was very popular both for research and for usage at some point. And we'll see that almost every DBMS vendor has incorporated it natively into the system. Can represent hierarchies. You could create document models with that. There are plenty of tools available for creation, parsing, searching, and querying. The downside is that it's a little bit bulky, meaning payload to formatting ratio is very high, meaning the payload is small, but you have to put a lot of formatting information. Parsing and search or querying can be CPU intensive. So that's another that plays into this, for smaller applications, smaller amounts of data exchange, it's not difficult, but if you want to exchange very large amounts of data in this format, and if you have to especially get it from the disk, then as we saw earlier, the IO cost goes up. And that is one of the reasons that DBMSs try to convert this into relations and various other things to avoid that. So here is an example of a XML that we normally use for reviewing a paper. So whenever there is a review of a paper from any conference, they send you these review templates, and it has the conference name, title, as you can see, uh, uh, summarize the paper's main contributions. So your answer is where you add your text, what you have to put in, and then you submit it. So this is, so you can see the formatting is very, there is a fixed format, rule for format, but it is pretty bulky. So one is the conference name, it ends with, so it starts with a less than and ends with a less than slash, submission, and everything has to match. So generating this is thing. Then once you generated it, and then this can be processed by a program automatically, and then it can generate the list of conference for the conference. So this is very widely used today for all conference reviews. So XML is also very widely used. So extensively researched on its usage. As I said, most DBMs support XML natively, meaning you can store XML as an attribute, as an object. And then you can parse that as an object. You can query that as an object. So there's a difference between storing natively versus, like, if when you store an image, they're not stored natively, they're stored as a file, which means that you cannot query it. You can only query the file name, but not the content. Whereas when things are stored natively, we can query them. Most DBMS support what is known as the document object model, which is the model used to create XML documents, and querying them using something called XPath. So this was very popular, and a lot of effort went into this. DOM is created in memory, so it has some limitations on how big a document you can do. Allows one to programmatically read, manipulate, and modify an XML document. Oops. So this is a data exchange format, which is quite widely used. So you can exchange any information in this format. And the tags, as we saw here, can be used as the vocabulary. So even though it's easy for humans to read it, so you can use these tags that are there, submission, question number, to interpret options, to interpret the data in some way if it is adhered to, and then so that will create the common vocabulary to be used. Okay, the second one is JSON. This is known as the JavaScript object notation. So this is supposed to be language independent data format. Even XML is language independent. Many programming languages support generation parsing of JSON natively. So again, this is a human readable and editable file. And this is slightly simpler to understand than XML, but it has some limitations as well. So it's also bulky, but the payload to formatting ratio is better than XML. Parsing and search can be CPU intensive, not as flexible as MLM for hierarchies and other kinds of things for separating them. So, but this is another one that is widely used. Here is an example. So this is an example of a JSON file, all text files. So it starts with this defines employee object, an array of 3 employee records. So start with the brace, ends with the brace. Brackets mean array, and then there is a tag, just like the options that there's a tag, first name colon the value, last name colon the value, and same thing. So they have syntax rules. Data is name value pairs, so you can easily import it into a dictionary, for example, in Python. Data is separated by commas. curly braces for object, square object. So this is a very popular format, even though this takes a little more space than because of the tags and other things, but this also helps in interpreting and understanding, but certainly a little bit simpler than XML. So I'm including this only for completeness, known as CORBA. This was an older data format that was used by C, C++, but it was extensively used in the 80s and 90s. I don't see much use of this today, except in older systems. So this is known as the Common Object Request Broker architecture, mainly used for interoperability. Was widely used earlier, although binary, so there's a binary exchange of information, includes protocol and architectural standards, so you can query from through the language and understand what it is. Supposed to be language and voice independent, compact data representation. So this does not have the bulk the other human readable representations have. Java supports it, open source versions available, but there is a high learning curve to understand and use it, not well supported by operating system vendors. Firewalls turning to use it. So this is just for completeness. So here are a few slides that talk about what USGS has done with respect to interoperability. So USGS data services gets over 1 million hits per day. OGS standards are used for geospatial information. So they have, from what I see, 30 plus standards that you have to pick and choose and use for a particular data representation in data formats. OGC conducted the interoperability assessment to see whether these standards are being followed or implemented by USGS servers, because these servers service a lot of people, and it's critical to make sure that so they came up with compliance testing, developing use cases and investigation of usability, development of CAT feed test suite. So all these were done with a project to make sure that the servers conform to the standards and hence the interoperable. So to conclude, data by itself is of limited use unless it can be found, accessible, understood, and can be used meaningfully. That's very evident from this discussion. Following the standards, using published data exchange formats with language support for them makes usage and analysis much easier and takes less effort. So that is the gain or the benefit to individual and society in conforming to the FAIR principles are one way to make data accessible and usable for millions of users as compared with years. Hence, it is critical, and we understand the importance of standards, integration issues, and why interoperability is needed. In the next module, we'll discuss metadata and other findings. So with this, I will wrap up this particular topic and answer any questions if you have before we start the next module.